So, welcome back, everyone. We're happy to have Lorenzo Orecchia today. Let me just start by announcing the next few talks. So we have, I believe, Sanjam Garg speaking in 2 weeks from today. He'll be talking about obfuscation, and David Stoyer will be speaking on December 4th. That's in 4 weeks from today. That will be 2 p.m. Eastern Time, so somewhat unusual. So today's speaker is Lorenzo Orecchia. Before we get there, let me just quickly go around the table. Not sure how well it would work now with the new Google interface. Those of you inside must have noticed this. They keep changing things here. Let's see what we have here. So there is, what do we have here? Thomas, you might have to help me.
Yeah, because I made a mistake and posted the link publicly. I now don't know everybody.
Okay, so we have lots of guests. I'll mention a few of them I know. There's Clément joining from the Columbia group. We have Yo Bridge who'll be joining from NYU. I see some of them. I see Jairam joining from Almaden, IBM Almaden. What else do I see here? Shaha from UCSD, and many others. So we increased the limit now to 15. Now we have many more participants. Should be fun. Okay. So I guess we just switch directly to the speaker. So today we have Lorenzo Orecchia. Lorenzo graduated from Berkeley about 2 years ago with Satish Rao, and he's now with MIT in the math department. And he'll be telling us about exciting developments in combinatorial algorithms for solving linear systems. So, Thomas, do you have anything else to add before we start?
Yeah, I would like to remind everyone that during the talk I might mute you. If you have a question, you have to unmute yourself. I cannot unmute you, so don't forget to unmute yourself. But we encourage questions, so feel free to ask questions.
Okay.
Okay. So thank you, Odad. Thank you, Thomas. Thank you to the organizers for having me. Let me know if there are any technical issues, and feel free to ask questions along the way. So I will be talking about a simple combinatorial algorithm for solving STD systems in near linear time. And this is joint work with John Kellner, Aaron Stitford, and Ziyuan Zhu, and we're all at MIT, either in math or in CSAIL, or both. So let me first explain what I even mean by the title. An STD system is a square system of linear equations where the matrix A, where the goal is to solve for x, and the matrix A has some restrictions on it, which are as A is supposed to be symmetric and diagonally dominant. We all know what symmetric means. It means that the bottom left entries of the matrix are a mirror image of the top right, and diagonal dominance means that if we look at any row or any column of the matrix, the diagonal entry in the matrix has absolute value that dominates the sum of all other entries in the row. So the most important entry by far in any row is the diagonal. Why do we care about this kind of matrix? Well, it turns out that these are a very important subcase of the larger class of PSD matrices. And they are a case which is particularly important in practice, and we'll see some example. And it's also interesting because it's particularly tractable. The fact that the system is STD immediately implies that the matrix is PSD, and it makes it finding the null space easy, so we immediately know where the matrix is invertible. And in some sense, that's why that process is easier than on general PSD matrices, and that's why we are looking for fast algorithms, while we would hope to find faster algorithms here. Okay, so what's the goal? The goal is to solve for x, and we assume that the right-hand side we are given, the B that we are given here lies in the image phase, so there is a solution. And we want to find an approximate solution, one which is epsilon away from the right one in the A norm. So we'll see why this condition makes sense. And the goal, the nearly linear time, refers to nearly linear in the sparsity of the matrix. So ideally, we think about a very sparse matrix, so there are lots of zero entries. And we want something that runs in nearly linear time, so linear times polylog factors in the sparsity of the matrix. And we also require a logarithmic dependence on the error. So it's a pretty strict requirement. It's basically asymptotically optimal up to log n factors. Okay. That's actually everything I'm going to say about STD matrices, because for the rest of the talk, you're going to reduce to a much easier case and one that we understand much better, which is Laplacian systems. So now, instead, our square matrix, instead of being a generic STD matrix, is a Laplacian. And we are trying to find a vector V that obeys this system of linear inequalities. And this reduction preserves approximation and sparsity up to multiplicative constants, so we can just worry about solving a Laplacian system. So this talk, I'm gonna get to the algorithm really in the second half. In the first half, I really want to develop an understanding of what Laplacians are and what the challenges and techniques are in solving these systems really fast. So let's quickly go and review what the Laplacian is. So we have a weighted undirected graph here on n vertices and m edges. Here n is 5 and m is also 5. And the graph Laplacian is a square matrix n by n, where on the diagonal we have the degree of a vertex. In this case, the degree of vertex 2 is 4. And on the off-diagonal entries, we have in the 2, 3 entry, for example, we have minus the weight of the edge 2, 3, so minus 3 in this case. So usually the Laplacian is seen as being the degree matrix minus the adjacency matrix. A better way to think about the Laplacian is as a sum of edges. So if you think about how each edge contributes to this matrix, you'll notice that each edge contributes its weight times this kind of matrix, and which has ones on the diagonal of the corresponding endpoints of the edge and minus ones on the off diagonals. This is the edge matrix, and the edge matrix is nice because it has rank 1, and we can really write it as the outer product of two edge vectors, 1 minus 1 on ij and 1 minus 1. And that will be the way that you're going to think about Laplacian as a sum of edge matrices. And once we introduce also these edge vectors that we call chi-e, we also immediately kind of assign an arbitrary orientation to each edge. You notice I put a +1 on I and a -1 on j. I could have done the reverse and got the same Laplacian. By doing this, I basically say that I think of this edge as going from I to j as the graph is still undirected, but when I talk about the space of edges, this is the positive direction and this is the negative direction. And this will be very useful when we discuss flows that inherently have a direction over the edge, even though they may go both ways. So one more matrix that we're going to need is the incidence matrix. And this is just taken by looking at all the chi-e for the graph. So all the edge vectors that form the graph and stacking them as rows of B transpose. And if we do this and we use the definition of L, we notice that L is just B transpose WB. And where W is just the diagonal matrix of weight. So B will be actually very useful because in some sense it's a square root of L. It's not square, it's n by m, but it gives us, it will be useful in understanding the Laplacian more. Okay, so let's, I think, go and see exactly what B does and why it's going to be useful. B acts on flow vectors, so on vectors that assign a number to every edge. And the result of B is that B transpose F, so remember B is n by m, so B transpose F is going to be a vector over the vertices, and the I entry of this vector is the flow out of vertex I and into minus the one into vertex I. So outflow minus inflow. So B transpose F is the net flow into the graph at each vertex. And the action on B on a vector instead is going to BV is a vector over edges, and it just tells us the difference between Vi and Vj along the edge ij. So these may be familiar for many of you. These are really useful in understanding the Laplacian as an electrical problem, which will be the perspective we'll be taking for most of the talk. So let's do that. Let's turn our graph into a circuit. We have resistances, and now our conductances over the edges 1, 1, 2, 1, and 3 actually do not correspond to resistances. They are the inverses of the resistances. The larger a weight is, the less the resistance is. So I'm going to take the inverses and think about the resistances instead. So we have these resistances, and we have the problem. We pick a source and a sink, and we want to send a current of flow into the graph, say of electrical flow, into the graph, say here at vertex 1, and 1 unit of current out of the graph at vertex 3. And the question is, what is the resulting electrical flow on the graph? And it turns out that this is determined exactly by two physical laws. Ohm's law, which says that the electrical flow should be the potential gap along an edge over the resistance, and the conservation of flow, which says that at every edge except the source and the sink, flow is conserved. So flow in equals flow out. And the first Ohm's law we can express in matrix terms in this way. The flow is the resistance, it's the voltage differences over the resistance. And the Kirchhoff's law is just that B transpose F is the net flow in minus the net flow out. So in this case, S is 1 and T is 3. And you can also allow more general demands that go from multiple vertices to multiple other sinks. But the main point is that by combining Ohm's law and Kirchhoff's law, we get that. So I have these two equations. I substitute for F, and I just get that the Laplacian of the voltages is the flow into the network. So that's basically why the problem of solving a Laplacian system is really an electrical flow problem. Is the problem of given a vector chi of flow demands, flow into a graph and flow out of a graph, find the voltage that is achieved by the electrical flow on this current input. And here is just a bit of notation. L is usually, it's singular. It has, we're just gonna restrict ourselves to connected graph. So L is gonna have one null space, one-dimensional null space corresponding to the all-one vector. And so it doesn't really have an inverse, but we'll be talking about its pseudo-inverse, which is just the inverse on the subspace in which L is invertible. So everywhere orthogonal to the all-one vector, and we're gonna denote it like this. So let me finish the preliminaries also by saying that there is an energy interpretation for all of this. So it's a physical problem, so you should also have an interpretation in terms of minimizing energy, and it turns out that that's true. So this system, LV equals chi, it can be seen to be the optimality condition for this optimization problem, which can easily be turned up to scaling to the problem of minimizing the quadratic form of x constrained such that x transpose chi is 1. This is really equal to minimizing the energy. So you see the voltage squared over resistance on every edge, the sum of that. for a fixed voltage gap. So if your chi is ES minus TT, this will just be a voltage gap of 1 between the source and the sink and minimize the energy. And we use the energy interpretation when we try to solve these systems approximately. Okay, so that's the preliminaries notation and kind of concepts that we need. Why do we even care about finding these electrical flows? Actually, so let me know if you have any questions about this background. I'm not hearing anybody, so I assume people are fine, but don't hesitate. Okay.
Yeah, so it's what do we need to remember of this? Do we need to remember Ohm's law or Kirchhoff?
Yeah, it would be helpful if you remember the two laws, but I will recall them when you need them. So, great. And the optimization I will also use again, but I will recall it. So, why does it matter? Why do we care about solving electrical systems? Well, it has lots of direct applications, and a few ones. I mean, besides modeling circuits, this is actually used to solve for page rank vectors that are very common in understanding social networks. But also, having access to an inverse chi tells us a lot of information about random walks on the graph. For example, a simple consideration is that one can actually spend L inverse as this following series, which is just each term is the lazy random walk on the graph for t steps. So in some sense, L inverse chi captures the aggregate behavior of a random walk over the graph. And for this, it has a lot of interesting applications, especially in spectral algorithms. It also has applications in numerical systems, and it's the basic primitive in the finite element method when we have a mesh and we try to compute a harmonic function over the mesh. Or smoothing, for example, is an example of that. Smoothing of images and computing eigenvalues and matrix exponentials. Those also have other algorithmic applications. So it's a very important primitive there. But I'm most interested in why this is a very important. It has become a very important primitive in theoretical computer science because it has led to faster algorithms for lots of important graph problems, many nearly linear time algorithms. And this has been dubbed the Laplacian paradigm, and it has led to faster algorithms for ST maximum flow, multi-commodity flows in a directed graph, sampling random spanning trees, and many more problems. And the idea is that really there are not many things we can do in nearly linear time, and it's surprising that we can solve a Laplacian system in nearly linear time. The other things we can do in nearly linear time are breadth first search, depth first search, sorting, pretty basic operations. And now instead we have the capability of assigning arbitrary positive weights to our edges, so arbitrary resistances, and solving a linear system in nearly linear time. It's a very non-trivial capability, and it does allow for lots of progress on many algorithmic questions. Okay, things are working. Great. My PowerPoint is being a bit slow. So what's known about this problem? So there are many different approaches in different communities to solving systems. So there are direct solvers that work for any matrix. The main simple method is Gaussian elimination, and it can be sped up by matrix multiplication algorithms, so recursive algorithms. And these algorithms all compute the actual inverse of the matrix, so they are slower, they take more than quadratic time. Then there are iterative methods that come from optimization that only compute the inverse on a single vector and work in general for PSD matrices. Examples are there is the power method, the simplest one I have not listed here, and then there is conjugate gradient and the Chebyshev method and variants of that. Then there is a large subset of heuristics that work very well in practice, multigrid, algebraic multigrid, and they work very well on subclasses of interest in graphs. And more to the point of this talk, of this paper, for STD and Laplacians, starting in the 90s, people have tried to get the learning time down, and eventually, in a landmark result in 04, Spielman-Teng got m polylog n, and this was later improved up to actually m log n, and tilde here hides log n factors. So it would seem like this kind of exhausts anything we can do unless we start trying to improve the log n factors. But what's problematic about the previous results is that the algorithm is really complicated, and its kind of complication has also kind of inhibited a bit its spread and the spread of these very nice ideas. And people have been trying to find an easier explanation of, an easier algorithm for this. And that's ultimately what we do in this paper. And our result looks like this. We solve this problem with linear system with the Laplacian in m log squared n with the right dependence on epsilon, and again the tilde hides log n factors. And they have a completely different approach. It doesn't require any of the previous machinery, and it's extremely simple. And the proof fits on a single blackboard. And the big advantage in practice that our algorithm has is that it's easy to show it's numerically stable. So even though the running time, as stated here, is worse than Spielman-Teng, if we look at the right computational model, we'll see that Spielman-Teng and the subsequent papers need to do arithmetic operations on arrays, on words that are very large. They are in polynomial size in the input. While our algorithm works well and in a stable manner without any change with words that are size log n. And this log to the Cn factor was not accounted in the running times given by the previous paper, because they used the computational model where they assumed a constant time for these operations. If we use a more realistic model, well, the time really depends on the length of these arrays which we perform arithmetic on, then we actually get a better factor of log n. So that's a big plus for our algorithm. But the real reason why I think this is interesting, it's because it's so simple and so different. And actually there is a philosophy behind the simplicity of this algorithm, and it's kind of it's gonna inform the rest of the talk, so I want to stop here for a second. And it is a trend that is much more general in the design of very fast nonlinear time algorithms, and that also applies to the recent results on STMFlow. And the idea is the following: that when we want to design a fast algorithm, we really think about 2 points of view. We want to have a representation of the problem which is nice, which allows us to do things fast. So not all representation of a problem in general are created equally. For example, the eigenvalue decomposition is a much nicer representation of a symmetric matrix than a generic basis. And constructing these representations often requires some combinatorial insight. And that's a big component in the design of this algorithm. And the other component is pick an iterative method that is very fast, that works well for this specific problem. And the theory community has really has been using and learning more about a wide body of results in continuous optimization, in gradient methods and randomized gradient methods and regularization to try to find better optimization routines to use in our combinatorial algorithms. And the main point is that we don't want to focus on a single one of these angles. We really want to integrate how we think about the problem representation and the iterative method we use. And we get efficient and simple algorithms when we make the right choice in combining these tools. And so this talk, we really kind of go over what these two issues are with the Laplacian system solving and trying to see why our algorithm does the right thing in combining these two points. Okay, so any questions at this point? So, okay. All right, so let's go on. And so I'm going to explore what the challenges are in solving Laplacian systems, keeping in mind this point of view of representation and iterative method. So the kind of basic approach to solving linear systems is one that involves changing the representation to one which is particularly simple, and that's Gaussian elimination. So Gaussian elimination in graphs has a very simple explanation. We take a node and we try to eliminate it. So say I want to pivot, I want to eliminate this node from the graph to make my graph simpler. What happens when I do the pivot is that I get a new graph where the node I eliminated is just a singleton. I don't have to worry about it anymore. But all its neighbors are now connected together. And you can unravel this transformation to see that this gives me a way of representing L as a smaller Laplacian and two matrices that are lower and upper triangular that are easy to invert. So this seems nice as long as we can perform these operations quickly. It's nice because eventually it will give us the exact inverse matrix. And there is also a bunch of freedom because choose which vertex to eliminate first. So in this example, I could have eliminated another vertex, and it probably would have been a better choice to eliminate another vertex. What's the problem with this approach? The problem is that the Laplacians that we get as we eliminate nodes can be very dense. So here I had a star, I eliminated the center node, and I went from four edges to 6 edges. And if you imagine star on n vertices, they will go from n edges to n squared. So if my Laplacian becomes very dense, I will just pay a large cost to be able to represent it. And that will make my algorithm very slow. So I need to do something. So people that have studied Gaussian elimination have tried to address this problem by picking the right elimination order. And that's why the combinatorial component of choosing the right representation comes in. How do we pick a good order? Well, we want to find a small vertex separator. If there is a small vertex separator, then we could eliminate on one side and eliminate on the other without any edges being created across. So if we can find a small vertex separator, then we can recurse on either side and hoping to keep the size of our Laplacians small as we eliminate vertices. And this approach is called the nested dissection, and it works very well when these small separators always exist. And that's actually the case for lots of graphs, like planar graphs are guaranteed to have square root n vertex separators that divide the graph into balanced components. So for example, this approach gives better than quadratic running time for solving linear systems on planar graphs. But it still has limitations because there are graphs clearly where all separators are large. So in a expander, a sparse expander, so an expander say with 4n edges, no matter what order eliminate vertices, we're going to get a dense graph at some point. So this really limits what Gaussian elimination can do. So that's really the big disadvantage, is that in the worst case we can know better than n cubed or matrix multiplication time if we are smart. So very far from nearly linear. So that's where the kind of representation stop approach gets stuck. But there are still some good takeaways that Gaussian elimination is very good in some cases. So if the graph is a path, or if it's a tree, or in general if it has low tree width, we can eliminate each node in time constant and then solve the system in O of n time. And this works in general for a tree. And we're going to exploit this fact that Gaussian elimination works very well on paths and trees. Something to keep in mind. It's one strength we have. The other family of methods, it's iterative methods, and they're really based on the idea of gradient descent. So gradient descent, we take our Laplacian system, and we saw that we could state it as an optimization problem. So this is this energy minimization problem I was talking about. doesn't really matter what the problem is. It's a convex optimization problem. So I can just go straight ahead and apply gradient descent to it. I will find just a quadratic function. So these are my gradients, and these are my gradients. And for convenience, the right norm to use is the green norm in understanding these matrices. And at every step, I do an update where I walk in the negative direction of the gradient because I'm minimizing on some step length. And the step length can be chosen in many ways. Just another choice, I think, is maybe half or maybe 1/4. There may be a type here. It's some constant depending on this higher eigenvalue here. Or for a quadratic function, the step length can actually be adaptive. We can minimize the function at every step. Whichever way we do, the kind of algorithm we end up with is one that involves truncating the sum of lazy random walks I had talked about. So the iterative solution that we get is the series up to t terms. It's it's the sum of t random walks.
Lorenzo, we have a question here from Jerem. Jerem asks, what is the degree norm?
Yeah, so the degree norm, thank you. So this matrix D here is the diagonal matrix of degrees. And somehow, it turns out that when analyzing the Laplacian, our concept of identity really should not be the usual identity, but it's more helpful to work with a norm that is scaled by the degree. The reason is really that the Laplacian is an object that is really defined over the edges. And the degree norm is the norm over the edges. There is a contribution from every edge, and it turns out that it's much easier to bound and understand the Laplacian eigenvalues when we normalize by the degree. So this is done, for example, when we talk about convergence of random walks and the spectral gap and so on. In particular, in this case, I think I did it because if you do it this way, the gradient step gives rise to the random walk. Did I answer the question?
I think so, yeah. Yes, okay. Thanks.
So let me know if you have other questions. I'm going too fast. It's very hard. It's hard to get feedback, so I appreciate any.
So can I think of the graph as being regular, so I don't have to worry about this D, or is that too much of okay?
No, it's fine to think about it being regular. And what happens is that kind of standard analysis of gradient descent tells us that the number of iterations that we need, so the value of t we need here, so how many random walk steps we need, depends on kind of the top eigenvalue, the condition number of the matrix. So the top eigenvalue over the minimum eigenvalue. And in this case, is 2/λ2. And this can be bad because for the path, for example, λ2 is 1/n². So we get n² iterations. And each iteration is a multiplication by this matrix, which takes O of m time. You need to spread the charge across every edge. So this running time for gradient descent on a path is very big. It's cubic. It's mn². And this is essentially tight, where we have a random walk.
We lost you for a second. Can you just say the last sentence once more? At least I couldn't hear it.
Yeah, sorry. We end up into this gambler's ruin problem when we try to make mass travel over a path. And it can go back and forth, the probability half. It can take up to n² and operate iterations to go from S to T, and each operation costs O of m, so n³. So that's really the limit for gradient descent, and we can try to be smart and do these accelerated gradient descent methods that are very popular. Nesterov method is the general umbrella for these methods. But for the quadratic case, you may know Chebyshev's iteration and conjugate gradient. And these help in the sense that the dependence on the condition number now is square root. So whenever we add, when we add 1 over n squared, now we have n. But still, if the number of iterations is n log n, the running time is still mn. So still way far from linear. And this is also not possible to improve really, because if you have to travel a distance of n, if you have a long path, it's going to take you n iterations to discover every vertex. So this is really the problem with gradient descent. However, notice that gradient descent works really well, both in the accelerated and non-accelerated case, when lambda2, the spectral graph, gap is large. So gradient descent works very well on expanders. So this brings us to an important dichotomy, which is Gaussian elimination is nearly linear on paths and trees, but slow on expanders. And gradient methods are nearly linear on expanders, but really slow on paths. So the main idea why people thought they could try to solve linear system faster, Laplacian linear system faster, was that the hope is that we can combine the strengths and the weaknesses of these two approaches to get a near linear time algorithm overall. So this is the idea of combining a representation approach and an iterative approach. And this was the first thing that work by Vadia in the 90s attempted to do this by using combinatorial preconditioning. So this works like this. We start with our system, and now we know we are very good at solving systems on trees and paths. We're using Gaussian elimination. So we modify our system to improve the condition number, so to make it better for iterative methods. And the way we do it is by multiplying both sides by the inverse of the Laplacian of a different graph, H. H is called the preconditional graph. So when we change the system like this, we're going to have a new matrix, LH inverse L. It's going to have a new condition number. And we can now try to apply iterative methods. And in the iterative methods we saw, each step is a multiplication by this matrix. And if we can perform it in near linear time, then we can run the whole algorithm pretty fast. And the idea is that if LH can be solved in linear time by Gaussian elimination, then this approach may lead somewhere. The well conditioning of LH inverse L will improve the iteration count because we'll get a better condition number. And the fact that LH can be inverted by Gaussian elimination quickly keeps each iteration linear time. So I think in 2001, it took a while. It took about, I think, maybe 5 to 10 years for people to settle down on using low-stretch trees as preconditioners, low-stretch spanning trees. And so clearly we want the graph H to be a good case for Gaussian elimination. So we're going to pick a tree. And what's a low-stretch tree? So we have a graph G. So here G is a tree, is a grid. And we pick a spanning tree. So this is the red spanning tree. For each edge, we can define the concept of stretch of the edge E with respect to the tree. And the stretch is, we look at the unique path between the edge endpoints along the tree. So this is the path. And we look at the length of this path. And here we think of length in terms of resistances. So think of resistances as length. The length of the path over the length of the edge. So how much does going from the graph tree distort shortest path in there? So the stretch of an edge in this case, the stretch of this is 5. 1, 2, 3, 4, 5. And some edges in this case are very bad stretch. This edge E should be O of omega of square root n stretch. So 2 square root n plus 1. The total stretch of a tree is defined as taking the sum of the stretches over all edges. So in this case, there are omega of n edges that are stretched by square root n. So the total stretch is n to the 1.5. Okay, so there's been a lot of work on low stretch spanning trees because they are a very important tool in embeddings and in approximation algorithms. The only thing we'll need is that it's possible to get m log n log log n spanning trees in time m log n log log n. So in near linear time, we can get a very good stretch, very low stretch spanning tree. And m log n is actually optimal. So m log n log log n is essentially optimal. So this seems it's interesting, but how does it relate to finding a preconditioner? Well, the idea is that the low stretch property actually allows us to bound the condition number of LT inverse LG. The idea is that because T is a spanning tree of G, we'll get that this quantity is at least 1. And the low stretch tree property tells us that the top eigenvalue of this matrix is the total stretch. And this actually, so I want actually to give a small proof of this. The reason is that the top eigenvalue of this matrix here, LT inverse LG, the way we analyze it is we bound it by the trace. So it's a positive, it's a PSD matrix. And its all eigenvalues are positive, so it can be bounded by the trace. Its top eigenvalue can be bounded by the trace. And the trace can be expanded as the sum over all the edges of G of this quantity, which is just the effective resistance over T, which is the length, the length of the path that connects the endpoints of the edge E along the tree. So this simple proof was devised by Spielman and Wu. And the main point I want to draw your attention to is that we really want to bind the top eigenvalue to get the condition number, but we use a trace bound because the trace is easy to get our hands on. And this will come back again a few times, and it's an important tool. The low stretch provides a trace bound that we use to bound the top eigenvalue. Any questions?
Can you explain again the last equality in the easy proof?
I'm saying there exists an easy proof. It's not necessarily that this is it. Okay. So here, what happens is I take our interpretation of LG as a sum over edges, and I guess I'm doing it for an unweighted graph. So then I can expand. Think of LG as a sum of chi transpose, and I get from this trace to this sum here. Now this quantity here is the effective resistance over the tree of the edge E. So if I have my red tree like before, let me go recover it. So I have an edge E. Its effective resistance over the tree is just the number of edges on the tree that connect one endpoint of E to the other. So it's the length of the path.
Good.
So the effective resistance happens to exactly the stretch. Here I took the unit weight, so there is no normalization by the length of the edge. But so it's a pretty intuitive concept. Yeah. So this may not be the simple way to write it, but the idea is that tree resistances are path lengths. So how do we use this? So Bowman and Hendrickson use this to give a runtime which is m to the 3/2. So square root m. So the condition number we saw is the stretch, and the stretch is roughly m log n. So the condition number is m log n. If we use our accelerated gradient methods, we get square root of the condition number, so square root m log n. And then each iteration has a cost which is O of m for multiplying by L, and O of n for inverting LT by using Gaussian elimination. So interestingly, if you actually don't use the condition number but combine conjugate gradient and the trace bound, there's a very nice result again by Spielman and Wu. The same approach and actually the same algorithm gives you m to the 4/3. And I don't want to go into how this works, but the main point is that you can get stronger results if you use the fact that low stretch is a trace bound and not just an eigenvalue bound. So this gets us down to m to the 4/3. How do Spielman and Teng manage to go beyond that? Well, it requires a lot of ideas. The fact is, low stretch trees are just not good enough. They don't have a good enough condition number. So what you do is they use better graphs to precondition, but then they run into the problem that it's hard to solve this system if G1 is more complicated than a tree. And the way they do it is they do it recursively. Then to solve G1, they find a new preconditioner, G2. And as they construct this chain of recursive preconditioners, every time they go one step down, these graphs become simpler, and some nodes get eliminated using Gaussian elimination. So in some sense, instead of separating iterative methods and Gaussian elimination, they mix them together. They do some preconditioning and some Gaussian elimination. Some preconditioning, some Gaussian elimination, and this fairly, this scheme magically gets a near linear time algorithm. It's a beautiful result. Still, it's not the most intuitive, so we hope to have a simpler idea of what's happening really. And the idea is going to be, we're going to use essentially the same ideas I presented, but combine them in a different way to get something very simple. So it is our algorithm at last. The first thing we do is we change representation. We don't try to solve for voltages anymore. We solve for flows. Instead of trying to minimize the energy, so solving for voltage was problematic because we ended up, when we tried to use iterative methods, these long paths were a big issue. Instead, we solve for flows, so we want to minimize overall flows, the energy of the flow, such that the flow sends the right demand. So minimize energy while routing the correct flow. And the idea is that now, maybe in the space of flows, we can use a representation where long paths are not a problem. Like, for example, one basis element in the space of flows could be this very long path. And so dealing with this might have cost 1 instead of n if I use the right representation. So flows give us different opportunities to get around this problem of long paths. So now that we restated our problem as a flow problem, let's look again at the optimization features of the problem. So let's go back to where we had Ohm's law and Kirchhoff's law. So when we did the voltage, we really eliminated F. We never worried about F. Now we're going to keep F around, actually. We're going to eliminate the voltages. We never want to worry about the voltages again. And the way we do it is, we want to get rid of Ohm's law. So there is an equivalent law, which is called the Kirchhoff cycle law, which says that for any cycle in the graph, if you look at the optimal flow, and you look at the sum of REFE over cycle, so the flow-induced voltage drop along every cycle, this should be 0. So it's saying that this quantity should be conserved over cycles. It should be 0. And it's not hard to see that Ohm's law, so notice the Kirchhoff cycle law doesn't have the word voltage in it. It's just a condition on the flows. And these two are actually equivalent. And it's easy to see that Ohm's law implies Kirchhoff's law, just because if you walk around the cycle, you must go back to the same voltage. The other direction is more interesting, and it's useful to see a proof. So here I do a graph, and I'm assuming the resistances are unit, and these are the blue values are the flow values. So I have 2 units of flow that's split here, and this should be a 2, I guess. All right. So there's a mistake here. Let's not worry about this part of the graph. Sorry about that. So the point is that, say, look at this cycle, for example. This cycle obeys the Kirchhoff cycle law, because you do 2, there is a drop of 2 here, a drop of 1 here, so a drop of 3 up to here. Now -1, -1, -1. So the drops along the cycle is 0. And yeah, and now we set. So if it is bug bothers you, imagine 1 unit of flow is coming out of the graph here. So there is 3 units coming in, 2 come out here, and 1 comes out here. So assuming all these cycles obey the cycle law, then we want to find voltages that obey Ohm's law. To do this, look at the spanning tree and use the spanning tree to define the voltages. So we start with voltage 0 here. There is a drop of 1 along this edge, so we put 1 here. A drop of 1, so voltage 2 here. A drop of kind of -1, so 1 here. And we got all these red numbers. They're the voltages of this flow according to the spanning tree. And now Ohm's law will be respected if actually on these off-tree cycles, if these off-tree edges are also fine, also respect Ohm's law. But the cycle property basically ensures that when we look at Ohm's law on these green edges, we get that it holds. So these two are equivalent, and so this proof also emphasizes that spanning trees will be important in our algorithm. So now we have the following optimization approach. So we want to find a flow that has the right conservation law, so it solves the right flow problem, and each cycle has 0 potential drop along it. And our approach is the following. The second constraint will always be satisfied. So we set an initial flow that gets the demand right, and we never touch that again. And then we just fix the cycles. We look for a cycle where this law is not respected, and we fix it. How does that work? So here is an example. We start with any flow that goes from S to T. So this one. And then we pick a cycle, say this cycle, and we look at the potential drop induced by the flow over it. So in this case,
what are the resistances here? Are they all 1?
Yeah, they are all 1. Yeah, thank you.
Okay, so I can know the RE. Okay.
Yeah, whenever I mention it's 1. Whenever, having non-unit resistances makes the examples hard because then you have 2 bunch of indices to keep track on. So let's look at this cycle. The potential drop is 1 along it, 0, 0, 1, 0. And the total resistance for the cycle is, so there is a violation of Kirchhoff's cycle law here. And to fix it, all we need to do is look at how long the cycle is. It has length 4 in terms of resistances. And we just send the potential drop over the resistance in the opposite direction. So 1/4 is 1/4. We send this flow in the other direction. And the resulting thing looks like this. And now you can check that on this cycle, the drop is 0. You get 3/4, -1/4, -1/4, -1/4. So 0. So this cycle is fixed now. We're not done because there are other cycles we need to fix. So in iteration, we might look at this cycle and fix it. But this is the main algorithmic idea. We start with any flow f, and then we pick a cycle and fix it and repeat lots of times. And there are a couple of questions I need. So this is the final solution, and there are a couple of questions I need to answer, which is how do we pick cycles? How many iterations do we need? And how we implement each iteration. Great. So we need the idea is that we want to have a large number, so near a linear number, of very cheap iteration. So we are willing to do lots of cycle updates, but each one is going to be very cheap. So, okay. So let's start talking about which cycle, how to pick cycles. And here the question is, we really want to have the right representation of the space of cycles. Right. So this is a geometric interpretation of what's happening. Here is the origin. Here is our starting flow F0. We just picked any flow. It belongs to the subspace, which is a subspace of demand that routes the subspace is a flow that routes the right demands. Then we want to move along the subspace. And at each step we take a cycle update. So in some sense, our moves all belong to the span of cycles. So we're always gonna start at F0 and move along the subspace of circulations, so which is the span of cycles. And so geometrically, you think of B transpose C equals 0 defines a subspace. So the subspace we move on is just a translation of this. So it's the space for possible cycles. And we really want to converge to this point, which is the point where the subspace of demand of flows routing the right demands intersects the subspace of electrical flows. And the idea is that because we always stay in this subspace, we only worry about this. This is going to be our universe. We never look outside of it. And we're going to look for the right basis to work on in this subspace. And the right basis of cycle space, it's easy to check that a spanning tree always gives a basis of the space of cycles. Thus, by taking the off-tree edges, so by looking at the fundamental cycles, take this off-tree edge will give this cycle, and this off-tree edge will give this cycle. And any circulation in the graph is a combination of these two cycles. So this is the kind of subspace of the basis we're going to look at. And for each E, I'm going to think about the cycle. For each off-tree edge E, I'm going to think about the CE as the corresponding cycle. So these are our basis vectors. And using this, we can rewrite the problem in this form. So my F0, I'm guaranteed gives me the right demands. I want to add something to it. I want to add a flow F to F0 such that I get my cycle law to be respected on all cycles. And my F is a circulation. My F is also in the sense that my F doesn't change the demands. When we use the spanning tree as a basis for the cycle space, we can rewrite this as finding a flow F, which is a combination of the fundamental cycles of the spanning tree. And when I add this flow F to my starting flow, the cycle law is respected. So now, in this formulation, I have m minus n plus 1 constraints, a constraint for every off-tree edge cycle, and m minus n plus 1 variables, because my flow is just a combination of these cycles. And this is the representation I'm going to work with. So start with an initial flow and then add with different weights each of the fundamental cycles to make the cycle law hold. Any questions on this? Okay. So our algorithm is cycle. Go ahead. Okay. So our algorithm then will iteratively fix the fundamental cycles of T.
So you're planning to end up with only log n at the end, or log 1 over epsilon?
Convert in terms of the running time.
How many cycles will we take? A combination is going to be a sparse combination of cycles?
No, we're going to change every cycle, but the point is that we're going to have m log n iterations, but each iteration is going to be really fast. So changing the cycle, changing the flow of the cycle is going to take log n time. So we can touch every cycle.
Okay,
but
I see.
It won't be sparse in this framework. But that's a good question, because we'll come to, there is another representation question to be asked there.
See, I think also Piyush has a question.
Go ahead.
It's a bit too far, so we can't hear you. Maybe someone closer to the laptop can say? Yeah, go ahead.
I'll repeat the question.
No, it's good, yeah.
The question is if Lorenzo could just explain how the set of cycles on the tree form a basis for the space.
Yeah, so well, the best way to see it is by looking at the matrices, maybe. So in this view here, this is the space B transpose C is a space of cycles, and you can check that it's the orthogonal complement of this space, of the space of electrical flows. And this space has dimension n minus 1, so the cycle space must have dimension m minus n plus 1, and the fundamental cycles of a spanning tree are m minus n plus 1, so we have the right number of them, and they are clearly independent. It's not possible to write this cycle as a combination of other fundamental cycles because you never include this edge. So we have m minus n plus 1 cycles that as vectors are linearly independent, and they live in a space of dimension m minus n plus 1, so they must be a basis. Does that answer Sushant?
So yeah, Piyush, I had to mute you because...
Is that fine, Sushant?
Yeah, that's good, thank you.
Yeah, great, thanks. Yeah, I kind of skimmed over that, but thank you for the question. So which iterative method is this? This method in which we fix a cycle at a time doesn't seem to be a standard iterative method. And I'll show that it actually is. The main point is that we are not doing gradient descent. The way gradient descent would work would be that we would look at our basis of cycles, and then we would move in the direction of the gradient. But the gradient could have a component along each of the fundamental cycles, so we might have to move all the cycles at once, which may be expensive. Instead, what this method is of fixing the cycle at a time is something called randomized coordinate descent. And what we do, what this method does, and you can, there's a nice paper by Stromer and Verschining that explains this, is that you choose a basis vector C, so a cycle with some probability. Here the probability turns out to be equal to the stretch of that edge in the 3 plus 1, and you move in that direction until, in this case, until your function, following the rules of gradient descent, basically. And then you repeat this. So basically, your coordinates now are cycles of fundamental cycles of the tree, that every step you move along one of these coordinates, and you use these probabilities to pitch. So the probabilities will be proportional. Probability that you pick a cycle and you move along it are proportional to the stretch of that cycle in the spanning tree. And the idea is that this exactly falls into this framework of randomized coordinate descent, and we have a convergence analysis for it that is exactly the same as for gradient descent. And it works like this. So imagine that this is our system now. Remember, this was the representation I said before. It's m minus n plus 1 constraints, m minus n plus 1 variables. So think of this, it's hard to write what the matrix actually looks like here, but let's call that matrix A. the usual gradient descent gives us this bound. It turns out that randomized coordinate descent, as I described, would give us this bound. So instead of the condition number, I have the trace over lambda mean. So this seems to be worse than the usual condition number by a factor of m minus m plus 1. But the point that that will not be a problem, because let's actually look at what these quantities are on our case. So there is a bit of algebra that I skipped here, but it turns out that this matrix A is really related to the spanning tree T again, and its minimum eigenvalue is just 1, and this is because the tree is the spanning tree, and its top eigenvalue can be again bounded by the trace, which is just the stretch of the tree. So somehow, even the same kind of calculation that worked for the voltage preconditioning holds in this case, and the trace of my matrix is the stretch of the tree plus a small quantity. Now we have our number of iterations looks like this, and we don't really have to worry about having the trace instead of the eigenvalue here, because the way we were going to bound the eigenvalue was by using the trace anyway. So we can just plug in our m log n stretch here and get that we need m log n iterations of randomized coordinate descent. So here the main idea again was that we exploit the fact that we have this trace bound in terms of the stretch of the tree. So we have a nearly linear number of iterations. How do we implement them? We want each of them to be really fast. We want to be able to.
Sorry, Joram just asked, how do you prove the convergence bound?
Yeah, the convergence bound. I was thinking about proving it, but then it's actually the same argument as for gradient descent. You can. It turns out that when you use, let me say a few words about it. When you use this probability, when you move along this coordinate with this probability, in some sense, in expectation, you'll be doing exactly the gradient step. So in expectation, you get the same benefit as doing a gradient step, except that that the benefit is divided by the ratio between the top eigenvalue and the trace. So in practice, at every step of this coordinate descent, you can get the same benefit. It's the same analysis gradient descent, except that your benefit is the benefit of gradient descent over the total stretch, and you basically go from the top eigenvalue to the trace. It's really the same analysis as gradient descent.
He also asked if this is similar to updates you have in multi-arm bandit optimizations.
So I'm not sure about. So does he have a specific paper in mind?
So actually, let's keep that to the end because we're running a bit.
Yeah, I'm almost done.
Let's keep these questions to the end. Okay.
Okay. Yeah, I'm almost there. Okay. So then define. So I just need to explain how we run these updates in time log n. And here is where we have another representation question. The main difficulty is that we may have a very long cycle, and to be able to perform the update, we want to be able to compute the potential drop along the cycle. And this seems hard because the cycle may be very long. And not only that, but then we also need to go over and change the value of the flows along the cycle. This is easy to do if the tree is balanced, because whenever we have enough tree edge and we check the voltages, we only need to go a depth of log n. So the update is easy to do when the tree is balanced, but what we can do when the tree is not balanced is we can basically use the same idea as nested dissection. The trees have very good separators of size 1. So we can decompose these trees recursively and have a representation of these voltage drops that is only log n sparse. And this is really the same idea as doing Gaussian elimination using nested dissection on a spanning tree. And the details are in the paper, but this is actually a very simple data structure. I just wanted to mention that it's kind of interesting that the same idea that goes into nested dissection makes our update be fast. Okay, so the resulting algorithm is just we pick a cycle using a probability proportional to the stretch, we fix it, we repeat, we need m log n iterations. Each iteration can be implemented in log n time, so we have an m log squared n algorithm. This can be improved. We can get rid of this log n term here in the error. And Lee and Sidford have used kind of the accelerated version of coordinate descent and get rid of also a square root log factor here in a very nice paper that appeared at Fox. And then, finally, my last slide, the open questions that are interesting for this algorithm are, can it be parallelized, and can we do it without randomness? We can show that any random order, so if we pick the cycles following the probability I talked about, with high probability, the resulting order of cycles works for any right-hand side. So most orderings of cycle updates will give the right answer, but we cannot exhibit any deterministic order that works. So that's a very interesting kind of question. And more generally, what else can we do by using this idea of having lots of cheap iterations? And a nice question is, for example, can we have a cycle update view of the recent results on ST-MaxFlow? The framework there is the same, but it seems hard to understand what the cycles actually are. And then I'm very interested in more applications of this combination of finding the right representation of the problem and the right iterative method to get better algorithms. And this almost linear time ST undirected flows are really an example of this, where the right representation is oblivious routings and the right iterative method is some kind of gradient, non-Euclidean gradient descent. So in conclusion, I think that these ideas, this kind of approach to solve flow problems can be very powerful. And yeah, and feel free to ask questions.
Okay, thank you, Lorenzo. And yes, we should move to some questions now.
Yeah.
And also, I should apologize. There was some audio problems. I hope it didn't bother anyone in the audience. We were trying to debug it yesterday, but couldn't quite do it. I think it was reasonably good.
Okay.
Yeah. So let me start. Jaram asked a question a few minutes ago. He asked, "How do you get a numerical stability property?" I don't think you mentioned that.
Yeah. So it turns out what can happen, the only way in which we need to analyze numerical stability is when we do cycle update. We may not, we might require a large precision if we want to fix the cycle completely, if we want to make the potential drop be exactly 0. But it turns out that that's not required by our algorithm. As long as we, say, decrease the potential drop by a constant factor along a cycle, we make enough progress. And that requires very basic precision. So the stability analysis is very easy. That contrasts with the fact that Spielman-Teng used the Chebyshev method, for which the analysis of stability is much more involved. Yeah, so I'm going back here. So my PowerPoint is very slow. Yeah, so when we fix cycle here, I've chosen 1/4 because it's what makes the potential drop exactly 0. But I could have chosen something near 1/4. As long as I made the potential drop decrease by half, the algorithm still works in asymptotically the same running time. So precision is not an issue.
This makes sense. Any other questions? I guess Jaram still had a question about the multi-arm bandit problems.
Go ahead.
If that's relevant.
Yeah. So
okay.
A lot of these updated techniques have an analog in online optimization and online learning. Coordinate, yes, some sure coordinate descent has been used in the community. I don't know the specific papers, but there is a very strong correspondence between techniques in continuous optimization and online learning. For example, the multiplicative weight updates that are very common in online learning and regret minimization are just an example of an optimization technique similar to gradient descent, which is called mirror descent. So these two words are really parallel, and I wouldn't be surprised if something involving coordinate descent also works in online learning.
Thanks. Yeah, in some sense, it's surprising that the coordinate descent it works so well, because it seems like you're going in the wrong direction. But you're saying in your case, because the trace and the largest eigenvalue are comparable, then maybe it's not that bad.
Yeah, exactly. In some sense, it's an artifact of our analysis that we don't have the tools to actually get any better bound than the trace. And once we use a trace bound, we might as well. Then, if we use a trace bound, we should really be using coordinate descent, because coordinate descent has the trace bound in it. So that's kind of where combining the right representation and the right iterative method comes in. If the representation gives us a trace bound, we should use an iterative method that relies on the trace bound.
Actually, if it's surprising that you can get such tight results using the trace bound,
There are graphs for which the trace bound is essentially tight. So, graph in which the congestion on one edge is really bad.